there have been a lot of changes going on behind the scenes with VSPAERO. You may have noticed that we haven't updated the solver itself in the publicly released version for a long time. And that's because there's been so much going on between Dave and I back and forth that we've really built up, honestly, 3 years worth of work that is all just about ready finally. And so on the OpenVSP side, I'm going to talk about those changes. Then Dave will talk about all of the VSPAERO, what's going on with it, and then I'll come back and I'll do a bit of a demo where we actually run the code after Dave's talks. Okay. So if you actually go and dig into the source code of a legacy potential flow codes, take PMARC, for example, you're going to find that a huge amount of the code, a large fraction of the code, is actually there for geometry generation. And this goes into what I talked about yesterday, where legacy codes had their own geometry tool built in. And it takes a lot. In fact, if you look at PMARC, there's more code for geometry generation than there is for the actual flow solver. So VorView was a geometry processor to take RAM files and turn them into Vorlax analysis files. And it had been integrated into OpenVSP 2. And Vorlax is a Lockheed/NASA Vortex Lattice code from 1977. And Vorlax is an interesting case because we used this with VSP before it was open. And the writing of Vorlax, 1977, predates the modern application of copyright to software. So Vorlax, by definition, was in the public domain. Unfortunately, it had been passed around from company to government and back to companies, and had been passed around for 40 years. And so when we were releasing OpenVSP as open source, the NASA attorneys didn't have an audit trail that they felt that they could really look at it and say, yes, we're clean. We have rights to release everything here. And we were trying to figure out what to do about this because we really wanted a similar analysis capability. And I had a student who was working on something called dgengeom that you're familiar with, and we'll talk more about that later. And Dave saw the dgengeom work and basically said, look, it'd be easier for us to just write a new Vortex Lattice solver than it would be to deal with the lawyers and get this cleared. And so that's what happened. So if you look back at old school VorView and Vorlax, we could take a RAM model like the one on the left, output a wireframe like this Hermite file here in the middle, and then process that using VorView into this flat plate over here on the right. And this is the kind of smashing and combining and slicing that it would do in order to create the geometry. And it worked fairly well in cases like this, or at least not overly objectionable. But when you would apply it to more complex cases, it would sometimes become unruly, as it would do this smashing process. If you wanted to keep the camber surface, that would keep some tangent angles like this. But you would often end up with nasty gaps between here, the wing and the side of the fuselage. And these nasty gaps would wreak havoc on the solution. Likewise, here, if we had a T-tail, you've got this huge gap down the body at the center, and this really just wasn't very satisfying, wasn't very good. So you would usually end up doing things like dropping the engines and dropping the empennage and just running a wing body, which would get the analysis to work okay, but it wasn't necessarily really what you wanted. So like I said, dgengeom was something that my student Joel Belbin did back in 2013, is when he finished his, presented at the workshop for the first time. And what it does is we can take each individual component and we can degenerate it. And we can degenerate to a surface, down to plates, down to an equivalent line, and even down to a point mass. And the idea was, instead of, most output files from a code contain exactly the analysis, exactly the information that one downstream analysis is going to need. And instead, with dgengeom, we took a kitchen sink approach, which is, let's put everything we can think of into this file, not knowing what it's going to be used for later. And, that's had some really interesting results over time. So VSPAERO was developed to use dgengeom originally to provide a vortex lattice type calculation for OpenVSP. The first dgen geom release that was public was with the first version of OpenVSP 3.0, which was in January 2015, and 3.1 included the first release of VSPAERO, which was really exciting. And the first time we ever talked about it at a workshop as a preview was in 2014. There's been lots of evolution, going from just a thin surface mode to a thick surface mode that we called panel mode. That happened with the first release of that in version 3.9 in August of 2016, along with the first workshop there that we talked about that. So then we had either a thick mode or a thin mode. So let's talk a little bit about the geometry in OpenVSP. Here's a very simple airplane, a pod wing with a vertical tail. And here we're just looking at the wireframe in a hidden view. And so you'll notice there's no intersection that's been performed at these joints. So we have a thick wing and a thick body, and there's been no intersection been done. We're just, the wing is passing through the fuselage. And that's just the normal OpenVSP wireframe. So when we would do degen, we would smash all these down to thin surfaces. And you see that the wing becomes this curved mean camber surface, and the fuselage becomes this cruciform, and the tail is a flat plate that then is coincident and overlaps with that vertical part of the cruciform on the body. And so in a degen geom, which is what VSPAERO was originally written to work with, no intersection calculations are performed between these. There's no trimming, there's no union. These are all just separate panels that happen to be, flying in close formation with one another, with no actual connection between them. When we went to the panel method, when we added that thick panel method capability, we used the output from CompGeom. And so here I've run CompGeom on this geometry, and you can see the first thing CompGeom does is it drops in the diagonals to turn all of those rectangles on the surface into triangles. And then we perform the Boolean operations, that Boolean union between these. And you can see we end up with this trimmed surface. So now we know the curves, we know the intersection between the wing and the body, and anything of the wing that was on the inside gets thrown away. And so we have an accurate representation of the OML. But the problem with this is we end up with some really low quality triangles. We end up with these really thin slivers along this intersection, along this joint, where all of these things come together. But this is what we would feed to VSPAERO to do its analysis. And then what VSPAERO in panel code mode, what you guys are familiar with today, what it would do is it would try and go through and clean that geometry up. So it would do the best job it could with the limited information that was in the file to remove those diagonals and get some rectangles back. And then it would go along these joints and it would try and remove some of these slivers and try and improve this geometry inside. And you can see it's cleaned up, but it's not perfect. There's still some of these nasty thin sliver triangles. We have some places like here around the nose where we didn't remove the diagonal, and things where it just got a little bit confused or it wasn't able to do a perfect job. But it's not bad. It did, what it could. And then it would analyze this for the thick surface. So one of the things I've been working on lately is what I'm calling the Ngon mesh. So before, that mesh was made entirely of either quadrilaterals or triangles. And what I've done now is instead of having VSPAERO perform that cleanup after CompGeom, I do that cleanup in OpenVSP. And I can do a better job simply because I have more information. I have more information about where those panels came from and about what their origin was. And so what I can do is after we do that CompGeom and we have all the triangles, I can go back and I can remove diagonals to reconstruct triangles both into quads, but actually here at the intersection, I'm actually reconstructing it into a polygon of an arbitrary number of sides. And so just quickly looking at it, this polygon right here is going to have at least 1, 2, 3, 4, 5, 6, 7. It's going to have at least 7 edges to that polygon. And the nice thing is that this polygon shape, right, is able to really clean up that geometry. It's really able to get rid of all those thin slivers and distill it down to a much, much cleaner geometry and recover something that's really very nice. And the good news is that the way VSPAERO has been written is VSPAERO all of the fundamental potential flow elements that it works with are actually edge-based. They're not panel-based, it's edge-based. And so each panel is a ring of edges. And so VSPAERO is able to work with a multi-sided polygon just as it works with a triangle or a quad. And it actually already used this, for example, in things like the agglomeration that it does, where it groups a bunch of panels together. It would then work with the polygon that was the outer side of that grouped panel. So this is one thing that's been added to the geometry, is we're moving to this end-on mesh. And another thing that I worked on was the ability to do an intersection between a mixed mesh, so that here you see the wing and the vertical tail are being represented as thin surfaces, degenerate surfaces like we did before, but they're being intersected with a thick surface, in this case, the pod fuselage. And so now the wing, this degenerate thin wing, intersects, but whatever was on the inside is now trimmed and thrown away. And so now we have this combined mixed thick thin mesh of n-gons, of arbitrarily number-sided polygons. As an option, we also now have the ability that if you choose everything to be thin, so thin fuselage and thin wings, we can still do the intersection. And so here it looks a bit odd perhaps, but we've intersected the wing with the body. And so you can see they're actually now connected. And it's a little tough to tell, but actually the vertical tail has been intersected with the fuselage. And so there's no longer any overlapping triangles or any overlapping panels back here. The fuselage is actually cut out and connected to this vertical tail. So there's no longer any coincident overlap. Everything's trimmed, even though it's all thin. And this is just the geometry side. But one of the things that Dave's been working on is then being able to handle this on the analysis side, so that now the solver, VSPAERO, can work with these, and I'm going to back up one, can work with a mixed thick and thin geometry. It can work with this and perform a solution on this. And so the flexibility this gives us is in OpenVSP, instead of choosing that everything has to be thin or everything has to be thick, which was VLM or panel before, that now loses meaning. And we now can choose on a component by component basis, oh, I want these components to be represented thin, and I want these other components to be represented thick. And then I can combine them with this n-gon mixed mesh, feed that to VSPAERO, and VSPAERO can perform a solution on that mixed geometry. So there's some other little tweaks that we needed in this. So there's a feature that I'll show you here in a bit called cull orphans. And basically, here we have this is the thick representation, but this is a representation of a strut braced wing. And here you can see that we have the strut and this little jury, this little leg right here that comes together. And in this case, the strut was built a little bit carelessly in that the strut actually protrudes out the top surface of the wing. Now, normally, if this was panel code, I'd say, shrink that back down, get your intersections fully buried, and do the intersection, and the panel code will take care of it. But the problem with that is, well, what if you wanted to use thin surface representations for these struts and jury and the wing? If you want these to be thin, then it's basically impossible to get that intersection right? The advice of working with a thick surface, where I say just bury the intersection in the other surface and let it be deleted, doesn't work. And so if you just did a thin surface intersection without anything special, you end up with these little stubs. You'll see there's these little stubs that stick out of the top where the strut comes up, and then the jury protrudes out the top of the wing here, and it protrudes below the strut down here. And so these little stubs are what I'm now calling orphans. And orphan panels are thin surface panels that are topologically connected to one another, but not topologically connected to the rest of their component. So you can't, if you were to walk edges without crossing this green wing, you can't walk from this little area up here, the orphan, you can't walk the mesh and end up down here on the main part of the jury. And so those are orphan struts. And so the cull orphans option that I'll show you, it will then delete those. It'll delete all the orphans, and it uses one more filter, It does it based on the area fraction. So you put in a number, say 5% or 10%, and it'll then delete any orphans any orphan panels that are together less than 10% of the area of that component. So that way, if you have something like a T-tail where you have, two big pieces that would otherwise be considered orphans, well, they're both 50% of the area. So you can set that fraction so that you don't cull the T-tail. But if you do have little stubs like this that are poking through your intersection, you can trim those little stubs so that you can clean it up. And even though on the right, even though this is a thin geometry, you'll see that we have proper intersections with no protrusions and everything's trimmed to what you want it to be. So this is in what'll be released soon, and I'll demo this in a minute. I'm also going to tell you some things that are going to be released even later. But another thing that I've developed is the ability to write a multi-resolution NGON file. So what I've done here is on the left is something like that NGON I showed you earlier, where I've done that intersection. But what I've actually done in this case is each of these meshes represents a doubling of the mesh. And so we have 1, 2, 3 doublings. So there's 3 doublings over on the right. And what I actually do is I generate this mesh on the right first. I generate the fine mesh, and then I do the NGON processing. I do CompGeom, and then I do the cleanup so that I have a nice NGON mesh. And then again, since I have lots of information about where these elements, these panels all came from, I then go through and I de-res it. I remove every other grid point, essentially. And I de-res it from this finest mesh to the next one. And then I de-res it again to the next one. And then I de-res it again to get this coarse mesh. And what this allows me to do is I now have a family of meshes of the same geometry, but at different resolutions. And moreover, every node in this mesh, in the coarsest mesh, is exactly known as a node that was also in the finest mesh. And so the coarsest mesh, the node points that you see there, are a strict subset of the next finer mesh. And that mesh's nodes are a strict subset of the next mesh, and those are a strict subset of the finest mesh. And so I can actually write this multi-resolution information out to a single file where that file contains all 4 versions of this model, but all based on a single set of points, just using different connectivity information. And I can also specify in that file that lineage where, the coarse mesh has a certain set of panels, and then those panels are divided in 4 to become the next finer mesh, and those panels are divided in 4 to become the next finer mesh, etc. And we aren't using this yet. This is just a geometry capability that exists, but the idea is that we hope to be able to use this to be able to study the effects of mesh resolution in a VSPAERO solution, looking at estimating the error due to the mesh, and potentially someday we may be able to do something with that information. And it should be really cool. Now, there is a difference here. We have even though these 2 meshes look mostly the same, I want you to look here at the leading edge of the wing where it meets the fuselage. And it's interesting because on the left, what I have is that coarsened mesh, where I started with a very fine mesh and I coarsened it down. Whereas on the right is where I generated something at the same resolution and I just directly jumped straight to that mesh. And you'll notice on the left that this curve is sort of concave between the fuselage and the wing, whereas on the right, it's actually convex. And the reason these are 2 different solutions is because on the left in this coarsened mesh, these points along this joint, these intermediate points, are actually located on the surface of the finer geometry, right? They're actually located off of that surface. And so technically, this panel right here at the side of this fuselage is no longer planar. This panel is not planar. These points in this intersection come up out of the plane. Whereas when I jump to that mesh directly, that coarse mesh directly, this panel is actually planar, and these panels are all planar, and so we get a different intersection. So that's probably subtle. It probably won't matter for you, but it's just to note that, how we got to that model is a little bit different, and it does have some small differences that exist. So that was pretty much the presentation side. I'm going to go in and do a little bit of a demo for just a few minutes to just sort of show how working with this geometry stuff actually works. And certainly, if anybody has any questions in the chat, we can pop those up. And finally, I'll just put a little bit again of the roadmap here. We're talking about the geometry updates here. And then Dave will go for the next hour where he'll talk about the solver in a lot of detail, and then I'll come back and do a bit of a tutorial. So that's kind of the arc for this talk right now. Okay, so very quickly, I'll just add everybody's favorite airplane. I'll add a pod and a wing and move that back. And so, if we come into VSPAERO now, and this GUI has changed from what you're likely familiar with. We'll talk more about that later. But without running the solver, if we just want to prepare to run the solver, this will just do the geometry and write the input file. So I'll just do that. We'll prepare the solver, and you'll see that right now in that first run, what we did, and let me come in and just delete the plane. There we go, clean that up. So here we have that n-gon geometry. And so if we change it to hidden, what we were working with was we did the analysis on the shown set, which would be equivalent. Let's change that to all. But we looked at everything thin. And so both the fuselage pod and the wing were thin. And we actually performed that intersection like I talked about before. And so we trimmed out those panels that would have been coincident here and did that intersection to get that geometry. To change that a little bit, let's take this wing and make it coplanar. Let's just pull it up a little bit. And in fact, let's make the root airfoil. Let's give it some camber. Let's make it a 4412. And so that's just at the root, and we can prepare the geometry again. And this time what you'll see, since I moved it up and added that camber, you can see that it's a curved surface and it's now up off, and we perform that intersection. You'll notice that we also have to split this panel at the leading edge and at the trailing edge. We have to split it because otherwise you would have one panel that would wrap around the top surface and the lower surface, and that wasn't going to be good for anyone. So what we do is we find that leading edge and we split it down to make sure that we have two panels, an upper and a lower panel at that leading edge. And back here, you can barely see it, but there's a similar little split at that trailing edge. Also, you'll notice that I've highlighted in red, I've detected the cut-a condition. I've detected the trailing edges. And so now OpenVSP is finding the trailing edges and feeding those to VSPAERO for it. So what I can do is I can come in, and in this case, I'm going to come to the pod, and I'm going to put that in set 0, and I'm going to come to the wing, and I'll put the wing in set 1. And if I want, I'm going to come into the set editor, and I'll come to set 0, and I'll change that name to thick. And I'll change the name of set 1 to thin. And what that allows me to do is I can then come here to VSPAERO, and I can tell it on the thick set to use the thick components and on the thin set to use the thin components. And now when I prepare the solver, you can see we've done this intersection, and we have a thin wing with a thick fuselage. And so we've done that and trimmed it down and are ready to send that over to the solver. So we have a few other options. I'm not sure if these are going to make the release version. We can come in here and we can manipulate that n-gon mesh. I can triangulate it. I can, dump out some files, and I can, show whether the edges are manifold or not. I'm not sure if this will make it in. But for example, if you show those non-manifold edges, it's just doing a quality report where it's going in and checking that, all of the normal edges. So basically any edge that has two faces adjacent to it is not highlighted. Any edge that only has one face is a boundary edge, and so that's in blue. And any edge that has three faces is shown in red. And so, along the wing, there's these edges that have, you know, a top fuselage panel, a bottom fuselage panel, and then a wing panel. So those joints have three faces associated with them. Likewise, you can come in here, and these are experimental features right here. So at least in the near term, the refinement will not be in the publicly released version, not until we're ready to do something with it. But if I want to come in here and say do, you know, 3 refinements, I can prepare that geometry, and well, maybe that didn't work. Maybe I've got that turned off already. So yeah, I've got that turned off. So I'm gonna have to go back and fix that for Dave, but not for everybody else right now. So I'll deal with that later. Let me open up that model and just show the cola orphans real quick, just so that people can see what I'm talking about on a real model. So here, and again, I'm going to get rid of the cutting planes on the center line just so that we don't have to look at that. So here's the model as it starts. And I can come in and you can see that this was very quickly put together, or put together with the jury that protrudes just out of the lower surface a little. It's nicely buried in the upper surface, and then it pokes out the top of the wing. And again, the reason this was done was just so that the strut and the jury and the wing. There we go. Let's get rid of. Let's just do these, and we'll do them in camber. Let's see if this works. There we go. So if we look at them in a thin representation, you can see that if we were to do this intersection, they would protrude, and we would have these, you know, dangling extra panels. And so that's what the Cull Orphans option is all about, so that when I prepare that solver, we're going to go through and go ahead and we'll do that intersection, but then we'll trim and we'll throw away those little remnants. So we have that kind of an intersection that is more likely what you want in that case. So that's pretty much what I have to say about the geometry modifications that have happened on the OpenVSP side that then feed to VSPAERO. Again, I'll do a demo of this version of VSPAERO later. And in the meantime, I'll take any questions quickly, and then we'll turn it over to Dave to talk about the solver side.
All right, we'll let the chat catch up in, say, the 15 seconds or so to get everything caught up. But haven't seen any questions posted just yet. And we've got a couple of minutes here before we need Dave queued up. So we'll see if anybody has any lingering questions here in the chat. There's a couple. Okay, so Rob, if you want to address those, we'll see if we can get switched over to Dave.
Yeah, so I see Andy asked, why might you want to do a mixed thick and thin model? And that's a great question. What I find is, number one, the thin solution is faster than the thick solution. You have half as many panels on lifting surfaces. You also, of course, a trailing edge, by definition, you're going to have a top and bottom panel that are very close together, and that can cause issues in the solution and in the solver. And by going to a thin surface, you get rid of those. So what I find is that for lifting geometries, for lifting surfaces, for wings and propeller blades, the thin surface often gives a better solution than the thick surface, and it certainly gives a better solution than you have any right to expect. It does a really good job. The thin surface does great. And but what I find is that it's sometimes unsatisfying when you work with a fuselage. You know, where that wing body join happens, representing the body as a thin surface isn't necessarily, you know, very representative. And for example, putting a nacelle downstream of a propeller, the main thing that nacelle is doing is acting as a blockage and pushing things away from the slipstream. And so when you put that, if you represent it as thin, it's not providing that blockage at all. Whereas if you make it thick, it can provide that blockage. So in practice, what I will probably do is I will usually represent, like I've shown in this one, lifting surfaces as thin and non-lifting surfaces as thick. And I think that that'll, lead to more realistic simulations. Now, you followed up with the question about the thick surfaces like the fuselage produce lift or just moment. So right now, they only produce moment because they don't have a sharp trailing edge with a cut-a condition on them. And so they still only produce moment, just like a thin representation of that fuselage. There is something that I've been working on for Dave to put in a limited wake at the trailing edge of thick bodies so that we can pick up where is the tail end of a fuselage and, how do we represent that? And Dave's going to work on integrating that so that we have basically better lift carryover from one wing to the other, and also some ability to, put a separation point at the tail end of a fuselage back here in a way that makes sense for that model. So when that happens, when you start to put a wake on the back of a fuselage in some way, then yes, it will start to pick up a load. It'll carry a force, not just a moment. But without that, without a wake off of a body, basically the only place you're going to get forces is where there's a wake, and otherwise things just contribute to moment. I'll let Dave answer the question about thick components and supersonic analysis. I think that's something that he has some experiments with, but isn't ready to go yet. But I'll let him get a little bit more on that, and I'll go ahead and maybe answer any other questions in chat as Dave takes over the talk.